afternoon session will be given by Mr. Hainzl of the University of Tübingen on microscopic derivation of the Ginzburg-Landau model. So thanks a lot. So, the thing is turned off. Okay. Then I have to turn it on if I'm. So better like that. Okay. So thanks for giving me the opportunity to talk here. So I'm replacing Edwin Landmann. So maybe the idea of the organizers is that the number of Austrians speaking here is a conserved quantity. So in fact, I'm speaking here about something which is not relativistic, but I hope you might be interested anyway. Namely, I'm talking here about a joint work, which is a joint work with Rupert Frank, we're sitting there, and Robert Seiringer and Jan Philip Soloway about some recently published work. So I will discuss how the Ginzburg-Landau model of superconductivity arises as an asymptotic limit of a microscopic model, which is called our Bardeen-Cooper-Schrieffer model. And this in some sense I just want to mention this in some sense is astonishing, because one thing, namely the Ginzburg-Landau model, which was established by Ginzburg and Landau in 1950 in order to give a first kind of phenomenological description of superconductivity. So the first kind of mathematical description, which was a purely phenomenological model. And the Bardeen-Cooper-Schrieffer model is a microscopic theory, which really has into account that the underlying electrons interacting in the field. But still, you can make the phenomenological model of Ginzburg and Landau really arises from the microscopic model. And the asymptotic limit is a semi-classical one. So for those who like semi-classical analysis, something also for you there. So, and let me just mention that the Bardeen-Cooper-Schrieffer model, which I will describe later, can be deduced from quantum mechanics, but here I use the word deduced because you can derive it formally, but a rigorous understanding how this model comes up from quantum mechanics is not yet done. So this is still a challenge. I think there are several people who tried for many years but didn't succeed so far. So let me describe the Ginzburg-Landau model first. This is a very popular among mathematicians, and I wrote it here in a form where just imagine that you have a box. Let's say a box of size 1, or so a piece of metal of size 1 meter, if you want, in each side. So a cube, and then you have some external fields which you produce in a lab, maybe an external electric potential and an external magnetic potential, and then there is a corresponding Ginzburg-Landau functional. Maybe you might not be used to see so many constants here, namely I wrote here B1, B2, B3s. This will have some reason which come out later. Namely, I want to show you that this thing is something which you get as a limit from an underlying microscopic system. Then of course the microscopic parameters of the system have to enter somewhere, and how they enter are just in these parameters which are written here. So this is the usual, apart from the parameters, this is the usual Ginzburg-Landau model. Namely, here you have the kinetic energy. So here you have the external potential A. So now the 2 already is put here on purpose, because at the end, I will tell you what psi is. Psi will stand for a kind of Cooper pair. It will be described a pair of particles, and since there are 2, this accounts for a 2 in the magnetic field. So for the same reason, there should be also a 2 here. But however, so now this is kind of an external electric potential, and here is this nonlinear potential, which is this I wrote it in this way, which is this Mexican head potential. If you want, you can write this something like that. So where at 1 and minus 1, this is just minus 1. Just minus 1. So now one of the main questions is, what is psi? So first of all, let me mention that in the mathematics literature there are many papers about Ginzburg-Landau functionals, and there are several books. And I think they started maybe with Precis and co-workers, and there is now a book of Fournier-Helfer, who studied how big has an external potential to be such that superconductivity breaks down. And then there is the work of Sandier and Serfati about vortices. So now the main question is, what is psi? What is psi? So maybe the idea of Ginzburg and Landau was that superconductivity should be described by some effect where you have many particles. So you think of your metal, you have many electrons, and superconductivity should mean that all the electrons should kind of play together. So this is maybe in the book of Leggett. In a book of Leggett, he describes superconductivity in the following way. He says that think of a big shopping street, maybe closely before Christmas, and then you're standing high up and you're looking down at the people running around, and then of course if they go shopping, they run around randomly. So if you will try to pass through the masses, you have some problems, because you will scatter from time to time with some people who run the other direction, and so you have some problems to run through. So but what is superconductivity in that sense? It is when kind of the army is marching through, so that everybody so they're really correlated, such that if the general in front says now go faster, then there is no resistance. And this basically, I think, was the idea of Ginzburg and Landau, that this ability to have no resistance can be described by a macroscopic wave function. And this macroscopic wave function here is psi. So psi equal to 1. So if A and W are 0, then you can check here. I mean, if A is 0, if W is 0, then of course, how should the minimize of this function look like? Here is the gradient, so psi wants to be, this should be 0, so psi wants to be constant. And then look at here, this potential. This, well, this doesn't look very symmetric, but psi wants to live exactly here, namely where psi is equal to 1. So the minimum is where psi is equal to 1, and psi equal to 1 means you have full superconductivity. And then if you turn on your external fields, the superconductivity breaks down, and if psi is 0, this means that you have no superconductivity, meaning that there is no correlation between the particles in some sense. I think this was the basic idea of Ginzburg and Landau, which even goes back to London from the 30s, who suggested first that should be a quantum mechanics effect. Okay, so what does this have to do with the Bardeen-Cooper-Schrieffer theory of superconductivity? We will derive this, and I actually have to say in the physics literature, there was already, so in 57 was the year when Bardeen-Cooper-Schrieffer came up with their microscopic theory, and in 59 or 60, Gorkov already argued that Ginzburg-Landau you get that as in a certain limit. So what we are doing here is we really give a rigorous proof, and we extend it also to more general situations, and we also do it on the level of a functional. He only did it on the level of equations. Okay, so we will derive this in an appropriate limit, and what will be the limit? The limit will be that the temperature has to be close to the critical one. And this kind of is not surprising, because when you look at what Ginzburg and Landau did, they usually asked what is the situation shortly before the superconductivity breaks down. So they kind of see it as a perturbation around small psi. So, and it breaks down close to the critical temperature, and there we really can give a rigorous proof that kind of Ginzburg-Landau follows from the microscopic theory. And of course, what we will also do, we will assume that you think of your box, you have external forces which you produce in a lab, but the length scale on which the particles interact are much smaller. So this will be the main, so you will have the small parameter will be the relative length of the small interaction and the macroscopic length, and the closeness to the critical temperature. I will tell you what the critical temperature is in a few moments. So first I want to write down the BCS energy functional. Basically in a form which already was done by Badin, Cooper, Schrieffer themselves, just formulated in a more mathematical way. And maybe the first time it was written in this way was maybe by Bach, Lieb, and Soloway in the 90s. So I have to refer to a paper of Elliot Lieb at that day because today is his birthday, his 80th birthday. So therefore it's a good time to refer to him as well. So now let's look at this functional. The particles are represented by this big gamma. So big gamma can be represented by a 2x2 block matrix with entries little gamma and alpha. So little gamma is a one-body density matrix, and little alpha is a kind of expectation value of pairs. So this is what you see in the physics literature as Cooper pairs. Gamma and alpha are not independent because they, as an operator, this has to be between 0 and 1, which gives some restrictions among alphas and gammas. So now you might ask, how does this come out of quantum mechanics? So imagine that you take maybe just one word. Imagine that you take a big Hamiltonian. Let's write it like that. There's an interacting Hamiltonian where the interaction between the particles are described by this two-body interaction V. So maybe at that moment I should say, if you know, in superconductivity usually you're not using a potential like that. You're using a potential which is mediated by phonons, which is more of the form x prime y. So more a kind of trace finite rank perturbation. This is the interaction it's used in superfluidity, where you really have interaction of a two-body interaction. And actually the mathematics is more difficult in this situation, which we are looking at here. So starting from a many-body Hamiltonian where the particles interact via a two-body interaction V, you can look at the states in a Fock space. And so if psi is a state in a Fock space, and if you now reduce to particular class of states, namely so-called BCS states, psi, then this expression can be expressed by these two types, namely by gamma, which is just the one-body density matrix, namely psi a star x a of y psi, and alpha is just the expectation value of pairs. Let's say ax, ay. So the first reduction is take the full Hamiltonian and reduce it to a certain class of states. Of course, mathematically the main problem is why should that be even true? So this is just heuristics. I mean, this was the thing. This was the idea of Badin, Cooper, and Schrieffer that this pair function here is kind of enough to describe the full mechanism of superconductivity. And of course, the second approximation is that what you heard, that you throw away the exchange in the direct term, because as you can see here, there is no gamma gamma. This is simply by arguing that that wouldn't really change the mech. So the mechanism is usually mediated by alpha, and the gamma doesn't change a lot. This is not totally true, but for potentials which are very short range, you can argue that this is that actually the gamma-gamma interaction only kind of changes the chemical potential. So the chemical potential is mu. This is put in there such that we don't need to fix the number of particles. And so now, what is now the main question? The main question is, if you look at this functional, is for which temperature T does the minimizing state have an alpha not equal to 0? And alpha not equal to 0, and I don't want to argue that now, but alpha not equal to 0 immediately means what I said before, namely that you have a kind of you have a macroscopic correlation of pairs. As soon as alpha is not 0, you know that you have such a long-range order, that the pairs really listen to each other on a very long distance. So, like the example of the army before.
Christian, alpha 0 would mean Hartley-Fock state?
Yes. Yes. Alpha equals 0 would be just the Hartree-Fock state. So, and that's why, since you have, if alpha is not 0, you have a correlation of the particles over a long distance. This immediately tells you, gives you superconductivity in the sense that there is no resistance. So, but let me mention, so I forgot to say that the S here is the T. This is a T is the temperature, T times S. S is the entropy. So S of gamma is minus trace of gamma log gamma. So in general, this question here is really difficult because you see, if in general alpha and gamma, there is no need that they commute or so. So it's kind of hard to approach this problem because alpha is really a kind of two-body wave function. It's really a kind of two-body wave function. So asking that in general this is hard to answer. But there are now some cases where we can answer the question. The first two are simpler, and the third will be the case where you really assume, which is a physical assumption, that A and W live on a different scale than the two-body interaction of the particles. So this, in this limit, you can kind of approach that, because then you can expand and so on. Okay. So now the easiest question it's easy to answer the question what the minimizer is if V is not there. So if V is not there, then the particles are not interacting, and this is a non-interacting system, and you can immediately write down the gamma because you just need to you just have to minimize kind of for gamma. The only problem is here will be the entropy, and you can write down the minimum immediately, namely alpha will be then 0, and the gamma, the entries on the diagonal, is just 1 plus, is just the Fermi-Dirac distribution, namely 1 plus exponential of little h, and the little h is just the operator which is given, which stands here. So if you put here a little h, and then you minimize over gamma, then you see that the minimizer has to be of that type. A little bit more involved is the other is the second problem, which we can answer pretty well, namely the case where the external fields are not there. So if you have no external fields, if A and W is 0, And then you put in the additional assumption, which you can actually prove afterwards, which you actually can prove that this is the case, namely that you reduce to translation invariant states, meaning that gamma depends now on x minus y and alpha depends on x minus y. If you do that, so let's go back to the functional, if you do that, then you kind of can integrate out the x minus y variable, also the x plus y variable, and then you have then here is x minus y, and then it's no longer a two-particle wave function, it's kind of a one-particle wave function, and it's kind of now a nonlinear operator for a one-particle system. And this now one can study. So this problem now one can study, and actually this was the starting point of all this of all the work we did the last years, namely together with Eman Hamza, who was a student at UAB at the time when I was at UAB, and Robert Seiring and Jan-Philipp Soloway. We showed the following, namely there is now a critical temperature, and the critical temperature depends on the potential V, such that if T is smaller than Tc, then the minimizer is normal, which means that alpha is equal to 0. And that for all temperatures smaller than Tc, the minimizer has a non-trivial alpha. So in the sense we proved that there is a unique temperature, and the temperature can be described by a linear, there is a linear characterization. This is a little bit surprising at first because the problem is nonlinear. The problem is nonlinear, but if you ask for if the minimizer exists, then you get a linear criterion, which is which is due to the special nature of the functional. And the criterion is the following, namely there is a pseudo-differential operator which is of that form where kt is where the symbol looks like eta divided by the tanh of eta divided by 2t. So here the temperature comes in, and the critical temperature is so that at this Tc, this operator has 0 as lowest eigenvalue. Has 0 as lowest eigenvalue. So, and this is in some sense, if you look at the functional, not really surprising, because when this is the second derivative, this is the second derivative of the functional at gamma 0. So this is the first derivative is 0, and the second derivative, if the second derivative has no negative eigenvalues, then there is no chance that you can get down, that you can lower the energy. So the question is, can you lower the energy? Is there a state alpha not equal to 0? So can you lower the energy with alpha not equal to 0? And the second derivative with respect to alpha is this operator. And if this operator has a negative eigenvalue, you can always do that. And if it has a positive, it doesn't, you cannot. So the only surprising thing is that the if and only if argument here. Okay. And so just as a remark, the essential spectrum starts at 2t. So I can always talk about an eigenvalue at t equals 0, at 0, because assuming that the critical temperature is not 0. Critical temperature 0 means that alpha is always 0. That's just what I say. Okay. So now we just assume that we have a potential such that the critical temperature is really bigger than 0, and the eigenfunction of this operator is unique. This is what we have to put in as an assumption. We can prove the uniqueness, of course, for all potentials whose Fourier transform doesn't vanish. Well, actually, it can be smaller equal here. Just on some points, it has to be not equal. But there are sure many other situations. We can just only prove it for that. But of course, it could be that in some situations where you have too much symmetry, that it's degenerate. But in general, it will be the assumption will be just satisfied. This. Okay, so this is the assumption now, and that's the way how we characterize the critical temperature. Now let me just comment, now we put in the scale, namely this should now be a box or a cube of size 1, and the assumption is now that this should show the potential V living on a much smaller scale than on the scale where the external fields vary. So now I think of take a box of size 1. This is my macroscopic variables, and now my microscopic variables are on a much smaller, live on a much smaller scale. So the potential here lives on a much smaller scale. So I just want to bring in this scaling parameter h into the functional. I mean, this is just kind of easily done. We fixed the size. X is now the macroscopic variable. So therefore, since x is the macroscopic variable, I have to rescale my functional, namely I get here an h. The h describes that the gradient here describes the microscopic particles. So since I work in a macroscopic coordinate system, I need here an h. And I also assume that the forces, the external forces are small. So therefore I put here an h square. They vary on the macroscopic in the macroscopic variables, and V varies on the microscopic variable. That's why I put here an h minus 1. So now the functional is kind of set up, and now what we look at is a temperature T. We will fix a temperature T. The T is appearing here, such that which is close to the critical temperature, which we describe here. And the closeness, here the h also appears. We want to have one small parameter. So here we are h squared away from the critical temperature, and with the parameter here d, we put in a parameter d. This was actually the same parameter which was appearing in the Ginzburg-Landau functional. And yeah, so okay. So now let me come to the main theorem. Now let's formulate the main theorem. And the main theorem is now saying, so fix your temperature close to the critical one, a little bit smaller. Then there exist parameters which appear in the Ginzburg-Landau functional, which you saw before, and the parameters depend on V and on the chemical potential, because they have to depend on the underlying microscopic system. Then, if we minimize the BCS functional to leading order, of course we get the energy as if there would be no interaction. So we get the interaction of the free Fermi sea, if you want. And then the next to leading order is given by the Ginzburg-Landau functional with a parameter d, but this is just a parameter. And now you see I wrote it like that: -3 plus 4. Oh, we can see this is 1. But the reason why it's written like that is because on our box, when you think of in the macroscopic scale, the box is of size 1. In the microscopic coordinates, the box is on a size 1 over h. So h to the -3 is the volume, the size of the box. So the free Fermi is the energy here. The free energy of the gamma 0 is of the order of h to the -3. So the next order is of the order h to the 4, and it is given by the Ginzburg-Landau functional. So, but maybe more important for thinking about what the psi means, More important is what it means to a ground state, or we don't even need to talk about the ground state, we can talk about an approximating ground state. So, I mean, take a gamma which is very close to the infimum, which is very close to the infimum, and the closeness you can really simply describe by the Ginzburg-Landau functional. Then the alpha which appears in gamma, the off-diagonal alpha which represents the Cooper pair wave function, that satisfies that to leading order is given by what is written here. And what is written here means that in the x minus y direction and living on the microscopic scale, it is represented by this alpha 0, which was the ground state, which is basically the solution of the translation invariant problem, which was the ground state of this linear operator. And in the center of mass direction, it is given by the Ginzburg-Landau minimizer. So psi 0 now means the minimizer of this functional. So in other words, what is psi? What is the Ginzburg-Landau psi? It is the center of mass. It is the center of it is the way how the Cooper pair wave function behaves in the center of mass direction. So this describes the center of mass movement of the Cooper pair wave function, and it lives on a different scale. It lives here on the macroscopic scale. Mathematically, this also can be represented in terms of an operator of a symbol. So here you can write this is the symbol, this is the Fourier transform of alpha, and this is just psi psi of x. And this is basically kind of the thing which we also plug in. So here again, to emphasize the answer what psi is in Ginzburg-Landau, the center of mass motion of the Cooper pair wave function. This is the main message I can say here. So if psi is 1, then the thing behaves like the translation invariant system. And if you turn on your external fields, you will see the change here in the density in this part, in the center of mass direction. Okay, so sketch of the proof. So in fact, I will not do anything fancy here. It's just shortly after lunch. We just want to keep it low. I just want to say that, of course, how do you prove something like that? So first of all, you try to get an upper bound. So you take a trial state, and then you try to get the lower bound. And I just want to sketch how we did the trial state, because this was basically the main idea. The main problem here in this paper was somehow, it's also a little bit, although the ideas are simple, it's sometimes a bit technical, but the main problem is to formulate the problem. This was maybe the main problem, to get an idea how one can approach this. And we do this by a trial state, and the idea comes from the book of Deschênes, by something which Deschênes calls kind of Bogolubov equation, and the people now call Bogolubov-Deschênes equation. So I think how you call it will depend on if you ask a French or a Russian or I don't know or so. It might vary. So what is the trial state is take. Now kind of we double the space such that it fits to the big gamma. The big gamma is a 2 by 2 matrix. So we take the operator H delta. On the diagonal, this is just the operator with the external magnetic field and the external electric field. We take H and minus H bar, and on the off diagonal term we put here delta, and now delta is basically alpha times V. And this alpha is what I said before. This is the thing where you have alpha 0 on the psi 0, which is what you expect, what is your Ginzburg-Landau minimizer, and the alpha 0 in x minus y direction, which is the minimizer of this linear operator, or you can say which is the solution of the translation invariant problem, which is to leading order the same, because close to the critical temperature alpha 0 gets small. So they are, it doesn't matter what of these two you take, you get the same answer. So now you take this alpha, this delta is an operator in this sense. If you want, you take this as a symbol, then you make out an operator, and then you plug in, and then you create this object, and you do this by just using Cauchy's integral theorem. So you write down 1 plus e to the 1 over t times c, and then you have 1 over c minus h delta, and you integrate around the spectrum. The spectrum is the whole real line, because you have here a minus, so you just integrate around the spectrum, and that's what you... And then you plug into the functional. But actually you simplify the functional, then you... Well, I don't want to say anything about that anymore. So in the lower bound, for the lower bound, the main idea is that you compare the energy, let's say the energy of the normal state where alpha is 0, with f of gamma, and in this difference a relative entropy term appears. And we use a kind of a lower bound on the relative entropy, which basically goes back to a paper with Mathieu and Robert a few years ago. Basically there we prove already this part. We leave out this part, but the first part we do. So we give a bound on the relative entropy, where on the right hand side the thing only depends on a gamma minus the minus, so it if you the relative entropy of two operators tends here, you get the lower bound where it's quadratic, and you get here a term which is closely related to this operator k of t, which I showed you before. So here the operator k of t pops up. So in some sense we use this to get an a priori information that whenever you have a gamma which lowers the energy with respect to the normal state, then alpha has to be to leading order, has to look like. So we get an using this, I cannot put that up, we get an a priori bound that alpha x and y is really of the time alpha x minus y plus psi of x divided by h half plus xi, and xi is really of smaller order in h. This is what we get by this thing, by this inequality, and using this a priori information, then we go on and basically can again use our upper bound. But I just want to show you, whenever you have a relative entropy and you need a kind of useful bound, maybe you can look in our paper. Okay, so now I'm almost done. I just want to say you can also ask the following. You have your general functional, and now you want to know what is the real critical temperature, because I told you before that the critical temperature, what is the critical temperature in the translation invariant case? Now you turn around the question and ask what is the critical temperature of the full functional, and there we now can also we can give an answer, namely the critical temperature is exactly this critical temperature which comes from the translation invariant case, where the Tc is here built in this linear criterion, where it's so that this operator is 0 as smallest eigenvalue, and the error term, so the next to leading order, is given by a d. Now this d is exactly also given by a spectral problem, namely by the lowest eigenvalue of kind of a linearized Ginzburg-Landau operator. So basically by two linear criterions you can get how the critical temperature behaves. And in that sense, what's also interesting, that the external magnetic field is always lowers the critical temperature, So magnetic field lowers the critical temperature, but an external electric field can raise the critical temperature, because D can here have D can also be positive. Okay, so that's all. I'm done.
Thank you very much. Any questions or comments?
All clearness removed.
So why do you call this starting point as microscopic picture? Because you start from BCS, is that microscopic?
Yes.
Can you repeat the question, please?
Why he asked why I call it microscopic. This BCS is microscopic in a sense because the alpha and gamma represent the kind of the underlying particles, so the electrons in a superconductor and the kind of atoms in a superfluid. Because you describe here the interaction between these particles. The only thing what you do in this simplification is that you don't take all possible quantum mechanically possible states, but you reduce it to a certain type of states.
So where is the spin, for instance?
Okay, that's hidden. I didn't say spin is there. So you would have to take here a 4x4 matrix usually. But you can kind of, there is an SU2 invariance which we assume here on the states, but the spin is there, sorry. I didn't want to explicitly put it in there. That depends on the spin. So it is microscopic.
So you didn't derive this functional during the lecture. So is it does it contain all terms? Does it contain the exchange term?
Now this is what I said at the beginning. The exchange in the direct term, you make a two type of approximation. You take the whole quantum mechanics, reduce it to a certain type of states, this generalized Hartree-Fock states, and then you throw away the exchange in the direct term. But you can argue, actually this is what one of my PhD students are doing now. What you can do is if you take your potentials which are of short range, let's say compared to mu, then the exchange in direct term just kind of renormalize your chemical potential.
Yeah. So
really
in principle, could you redo this
No.
result, including the direct and exchange terms?
We didn't yet do that, but I say yes. Yes, but for if V is you have to bring in some assumption on V, that it is really, you have a V which is basically, I write it so like that, or let's make it more physical. So something like that, where this part is kind of small compared to some parameters here in the system.
So it has to have both a positive and a negative part?
Now the positive part is there because if you have the gamma-gamma interaction, you need a stability. The system would be very unstable if it's not repulsive when the things are close to each other.
So you need both parts.
You need both parts.
So
the idea is basically that take a potential like that, take L small, but fix the scattering length. If you fix the scattering length, then you can do that.
I mean, traditionally in textbooks, one just does not take a local potential, but
but this is for superfluidity. This is usually what you see if you look at systems of gases, where you look at kind of these Fermi gases which consist of atoms. That's basically what is used to model. They actually, in the physics literature, they go even further. They take a contact potential.
yeah, sure.
They take here a delta. In some, well, I mean, it's not a delta in 3D, but it's a contact potential. But as I said, I think if you take a non-local operator, things are simpler, because then you have a rank one, a finite rank 1 perturbation or so. Finite rank, but I mean, what usually the Baudin-Cooper and Schriefer did, if you count around the Fermi sea, it's a rank 1 perturbation.
Yeah. Could you redo your proof for this rank 1 model?
Yes. Yes, we can.
Maybe we stop at this point and thank him again for this.